Since you mentioned earlier the direction of time and time's arrows, but I held off on that for a moment. Maybe that's where we should get started when we talk about the application. So what does the Mentaculus have to do with time's arrows?
Um, Here's a way of describing sort of a path towards this general idea of this sort of architecture of our fundamental physical account of the world, which is what this Mentaculus stuff is supposed to be. Um, um, you start off you start off with things like the Boltzmannian account of a bit over 100 years ago, of the relationship between classical mechanics and thermodynamics. Okay, you have this idea that that things like gases are really large collections of particles, and those particles, if Newtonian mechanics is the fundamental law of the motions of material particles, those particles are obeying Newtonian mechanics. Those particles are bouncing around and smacking into one another in accord with the laws of Newtonian mechanics, and there should be some kind of account of the way large numbers of particles are going to smack into each other and bounce around in accord with the laws of Newtonian mechanics, that are from which somehow a description of the familiar properties of gases, the behaviors of pressures and temperatures and volumes and densities and so on and so forth, is going to emerge. Okay. And Boltzmann's big idea is that Boltzmann's huge achievement is to begin to make it plausible that the following is true. Okay. You take, like Barry was saying before, a typical macroscopic level description of an object like a gas. Okay, you have this large collection of particles in a box, and the boxes, the stuff in the box is characterized by these macroscopic variables like temperature and pressure and density and volume and so on. It ought to be intuitively clear that corresponding to a macro description like that, there will be many, 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 indeed an infinite number of, as it were, compatible micro descriptions of the individual subatomic particles that make that gas up. Okay. Small variations in the positions and the velocities of some small subset of those particles is not going to alter the overall macroscopic description. There will be many, many microscopically distinct ways of realizing a single macroscopic description of a gas like that. And Boltzmann has this idea that you can show that on some sort of sensible definition of most, or of the vast majority of the microstates compatible with a macrostate like that, okay, if you evolve them forward in time using the Newtonian laws, are going to give you the kinds of evolutions on the macro level that you're used to from your everyday thermodynamic experience. So, for example, if you have a macrostate which consists of a cooler body and a hotter body in thermal contact with one another, you look at all of the infinity of microstates compatible with a macro description like that. Okay. And there'll be a sensible sense of most, given that the macrostates are infinite. That may seem counterintuitive, but there are these measure theoretic senses of most. okay, in which the vast majority of the microstates compatible with that macro description, a hotter body and a cooler body in contact with one another, okay, if you evolve them forwards in time using Newton's equations of motion, are going to take you in the direction of those two temperatures tending to equilibrate with one another rather than to get farther apart. Okay, they'll take you in the direction of heat flowing from the hotter body to the cooler body rather than from the cooler body to the hotter body. And all of the Boltzmannian arguments are designed to make it plausible that in every simple thermodynamic case, something like that is going to be true. Okay. The entropy will statistically tend to increase, so on and so forth, where you're equating the relative populations of microstates that will do this and microstates that will do that macroscopically with the probability of the system doing this or the system doing that macroscopically. Well, is that clear so far? Good. So the idea is you can explain thermodynamic behavior. That is, Boltzmann makes it plausible that you can explain thermodynamic behavior. It ought to be mentioned that none of these results is fully general or fully rigorous mathematically, nowhere near it. The bottom line here is that we can't do these calculations. There are too many particles involved. We'll never be able to do these calculations exactly. No envisionable computer will ever be able to do these calculations exactly. They're just way, they involve way too much data.
Not even a quantum computer.
No envisionable computer is going to be able to do this. But Boltzmann has these very nice arguments which make it plausible initially that claims like the one I just made are true, okay? That the vast majority of the microstates compatible with a given thermodynamic macrostate of cold body here, warm body here, are going to lead, when you plug those initial microstates into the Newtonian equations of motion, to states where the temperatures equilibrate exactly in the way we see them doing in our everyday macroscopic lives. Good. This result is very impressive to people. Okay, this begins to suggest a way of drawing connections much more generally between physics and the special sciences. Okay, science is not only like thermodynamics, but biology and economics and I don't know what. That there's a general model here for analyzing the connection between fundamental physics and the special sciences. And the general model is going to involve adding to the dynamical equations of motion, the deterministic dynamical equations of motion, some kind of postulate about probability distributions over initial conditions in the way that Boltzmann did. Moreover, Boltzmann recognized that if you were to do your calculations about the future and the past just by taking the present macro state of the world, okay, putting this uniform probability distribution over all the microstates of the world compatible with the present macro state of the world, plugging those into Newton's equations of motion and calculating backwards and forwards, it would give you the wrong answer. Okay, it would give you good answers about the future. The entropy is rising, temperatures are equilibrating, things are wearing down, so on and so forth. But it would give you the exact same answer towards the past. In the past, things would be more worn down. I would look older than I do now, imagining that such things are possible. Paper would be
You look
yellower
like me.
in the past than it was now, so on and so forth. It gives you the wrong answer about the past. Boltzmann realized this as well. And so it looks as if in order to make this whole system consistent internally, both internally consistent with itself and consistent with our everyday macroscopic experience of the world and our everyday experience of the difference between the way the past looks and the way the future looks, you're going to need to add yet another postulate about the initial macro state of the world. This is the postulate that Barry and I call the past hypothesis, the third component of the Mentaculus. Boltzmann realizes if you add that, you've got yourself a good account of thermodynamics. Good. What's interesting is you play around with that for a bit. This addition of the past hypothesis, if you play around with it, if you draw out its consequences in the appropriate way, it turns out is not only going to give you an argument for the asymmetry between past and future that you find in thermodynamics. That is, as you go toward the future, temperatures tend to equilibrate. As you go towards the past, temperatures tend to disequilibrate. As you go toward the future, entropy rises. As you go toward the past, entropy gets lower. That's the thermodynamic time asymmetry. If you play around with this exact same past hypothesis, that's the one you find you need in order to underwrite the thermodynamic time asymmetry, you can make very impressive plausibility arguments that this same hypothesis about the macro condition of the world in the distant past at the beginning of the universe is also going to be able to underwrite what look on the surface like very different kinds of time asymmetry that we encounter in our everyday lives. For example, the fact that we have a very different kind of epistemic access to the past than the kind of epistemic access we have to the future. Okay, if I want to know what I'm going to have for breakfast tomorrow, that's a very complicated calculation I have to do that involves most of the elementary particles in the universe, or at least within my light cone, so on and so forth. If I want to know what I had for breakfast yesterday, it's the easiest thing in the world. Nobody needs any training in physics in order to do that. You simply remember, okay, what you had, or you look on the security camera video where you were eating, or something like that. We have a wildly different kind of epistemic access to the past than we do towards the future. It turns out, or at least I think it can be made very plausible, that this exact same past hypothesis that Boltzmann found necessary in order to explain the thermodynamic asymmetry will also explain the temporal asymmetry and epistemic access, will also explain the very different kind of the difference between the very different kind of epistemic access we have toward the future and toward the past. Moreover, there's a third kind of there's a third kind of temporal asymmetry, which we're running into all the time in our lives, what you might call a causal asymmetry, or an asymmetry of intervention, or an asymmetry of influence. We find that by acting now, and this is the very foundation of everything we think about ourselves as agents, and so on, we find that by acting now, we can influence the future, whatever exactly that means, in a way that we can't influence the past. Our capacity to influence things, our capacity to control things, also has in it a very profound time asymmetry, a time asymmetry which, like the thermodynamic asymmetry and like the epistemic asymmetry, is something enormously mysterious if the only part of physics you're looking at are the dynamical equations of motion. Because those dynamical equations of motion don't make any distinction between future and past whatsoever. They have this strict, precise, pure mathematical property of invariance under time reversal. Okay, so if you look at these asymmetries, all three of them, from the standpoint of the microscopic equations of motion, all three of them are profoundly mysterious. It's hard to see where all three of them could come from, because there's no way to even get a foothold on this from the standpoint of the microscopic dynamical equations of motion. They make no past-future distinctions at all. Boltzmann finds that by adding the statistical postulate and by adding the past hypothesis, he can take care of the thermodynamic time asymmetry, or he can plausibly take care of the thermodynamic time asymmetry. Other people find, since Boltzmann, that this same past hypothesis looks like it can also take care of the epistemic time asymmetry and of the causal time asymmetry. And you suddenly begin to get flushed with success, okay, and flushed with a sense of power. And you say, maybe this can take care of everything. Okay, maybe just these three components give you a complete probability map of the world. Okay, that's the sort of intellectual genesis of this idea. That's the route towards this idea. It very much depends on attempts to get to the bottom of these time asymmetries. So thinking hard about these time asymmetries and about what you would need to add just to the dynamical equations of motion in order to explain these time asymmetries is how you build this architecture in the first place. Once you have it, it begins to look plausible for all kinds of reasons that this is all you need to explain nature. Okay. Of course, when we talk about the dynamical equations of motion, we can talk about the specific example of the Newtonian dynamical equations of motion. We know those are false. We could also talk about the non-relativistic quantum mechanical dynamical equations of motion. We know those are false. We could talk about the relativistic field theoretic dynamical equations of motion. We're pretty sure, because of gravitation and because of problems with renormalization, that those are false. So we don't know yet what the true microscopic dynamical equations of motion are. That's a slot in this architectural structure that remains to be filled in, maybe by string theory or by brane theory, or I don't know what. Similarly, once we have the basic ontology of the world, when we know the exact microscopic dynamical equations of motion, and if we know they refer, say, to strings, that's going to lead to a more precise formulation of the statistical postulate and the past hypothesis in terms of those languages. So this is at the moment just a sort of a broad architectural structure with various slots in it, okay, in which you're supposed to place things that are yet to be discovered about the fundamental structure of physics. But when you're playing around with this, you're trying to make a plausible case that it looks like a general structure like that is going to be all we need. Sorry for talking so long.
Yeah, well, it was great, David. I have a few points. Can I make, Robinson, unless you want to?
No, absolutely.
David?
Go ahead.
Okay. So let's see, in order. One is the point that David was making towards the end about the fact that we don't know the ontology of the world exactly, but we do know how to describe the world macroscopically pretty well. it can be improved upon there too. We don't know what the dynamical equations are and so on. But as Sean Carroll points out, that pretty much any successor theory at the micro level has got to agree with respect to the macroscopic world with what, basically quantum mechanical, quantum field theory says about the world. It's only in very special circumstances that these theories run into trouble, that we don't, usually not in such circumstances, unless you visit black holes from time to time. The other point I wanted to make was when you're talking about the past hypothesis. So that's a name that David gave. It's a very good name, but I think it's also a little bit misleading in this respect. Of course, it's a hypothesis, but it's also a law. Furthermore, calling it the past hypothesis has led some people to think that the view imagines already supposing a distinction between past and future. But that's not true. Rather, it earns its name as the past hypothesis by doing all the work that David just described.
Yeah, that's an important point. Yeah.
And the last thing I wanted to say this, I started off being a philosopher. We didn't get into this. David started being a physicist. So he doesn't have the same background in philosophy with the same sort of worries about philosophers, the same interactions with philosophers that I have. But, the epistemologists are all around me. Action theorists are all around me. David's time and chance makes the most important contribution a more important contribution to epistemology for the reasons he said, by explaining the epistemic asymmetry, and to action theory by explaining the asymmetry of influence, than pretty much any other discussions in these areas. I don't mean to make a competition, but it should be something that's on the philosophers' reading list so that they understand what's going on. They just sort of, in general, it's just sort of presupposed, or it's not even a question that's asked in epistemology. I'm not sure if epistemologists ever really bothered to ask the question why there's this epistemic asymmetry, except they sort of thought there's a causal asymmetry that must be responsible for it, or something like that. But the Mentaculus explains all that. The last thing I wanted to say is this: when David was glowing, waxing very poetic, and saying, now you look like I have a whole theory of the world, I then remembered the movie, and meant I should have said earlier that the person who gave it this name, the Mentaculus, in the movie, is clearly out of his mind. Okay, but we mean this seriously, to be taken a serious proposal about the world, serious enough to be, criticized, and there are criticisms of the whole story, but I think it is very serious and very, very, very exciting to me, at least, as a comprehensive view of the world. That's a kind of, a theory of everything that's also operates at the macroscopic level as well.
Just to expand a little bit on what Barry just said, there is a big obstacle to teaching this stuff, and a big obstacle to communicating it successfully to other areas of philosophy, traditional epistemology, traditional action theory, so on and so forth, is getting people in a mood where these time asymmetries even arise as a question. Okay, it's not immediately easy to see why it isn't analytic, as it were, that memories are memories of the past. Okay, that of course we have a different kind of epistemic relationship to the past than we do to the future because it's the past. Okay. And of course, we have a different kind of relationship vis-a-vis capacity to control or influence the future than we do to the past, because the past is done, because the past is finished, because the past is locked in. Okay. And the idea that None of those notions of being done, of being locked in, of being the past are there to be found in the fundamental equations at all. Okay. And you have to really focus on that to get yourself to feel that there's a question to be addressed here at all. The harder part is not answering the question, it's asking the question in a clear way. It's so baked in that it's hard, that these things are somehow analytic to what you mean by past, or analytic to what you mean by memory, or analytic to what you mean by control or influence. And the mood you have to get yourself in, okay, is like, I mean, this is what I always tell students. You have to imagine that you suddenly discovered that by, that you have a very different kind of epistemic access to things to your right than you do to things to your left. Okay. Or you find that by waving your arms around here, you can have profound influence on things to your right, and you have no influence at all on things to your left. Okay. If it occurred in that way, that spatial way, rather than a temporal way, it would be obvious to everyone that there's a question to answer here. Why? What's going on? What's the asymmetry here? What's preventing this influence from propagating to the right just as it propagates to the left? What is it that's preventing me from getting information from the right just as I get information from the left? If you sort of focus on that, it'll become obvious, number one, that there's a question here, and number two, that this is a question to which physics, not pure philosophical reflection, ought to be, to which we ought to turn to physics to answer, and to which physics owes us an answer.
Mm-hmm. That's great.
That's my little sermon about that.
That's great, and a beautiful way of making it very, very vivid. But philosophers thought that metaphysics was going to answer this kind of question. But
nobody would think that metaphysics is going to answer the kind of question I just described.
Absolutely. That's why it's so nice way to put it, in such a vivid way to put it. So philosophers have now given lip service ever since Quine. You're not supposed to think that meaning is going to answer the question, as you were suggesting. Since Quine, we were supposed to naturalize metaphysics, but take that seriously. That means, as Dave was saying, physics should answer this kind of question, not by having some sort of metaphysical view about time, which somehow makes it the case that the past is different because it has a different status in reality or existence, or something like that. And I'm sorry to hear that Lee Smolin, I don't know if Lee Smolin thinks about these kind of questions like that, but I don't know whether he thinks presentism could help with any of these at all.
No, Lee definitely has a very different view about this. Lee wants to find a place in fundamental physics for passage and flow, and yet Lee is working from a very, very different set.
So how does the presentist metaphysics
initial presumptions? What did you say, Barry?
Well, Robertson said, and I knew this before from Lee, that he's a presentist about time. So are you saying that he's not going to appeal to that to explain any of this phenomena? That would be a reasonable thing to do. And I wonder, why is he a presentist?
No. He is going to appeal. No, he's going to think. I don't want to speak for Lee, and I'm not sure I understand the view so well. What I do know about Lee is that he wants to find a place in fundamental physics. Okay, this is not something in a picture like ours. All the talk about flow, all the talk about passage, so on and so forth. This is going to be analyzed. We're going to give an analysis of this in terms of these various asymmetries, epistemic, causal, so on and so forth, the buildup of memories as time goes on, so on and so forth. And those are in turn going to be explained in terms of the three fundamental physical postulates of the Mentaculus. And so at a fundamental physical level, these words like flow and passage aren't going to appear anywhere. What I know of Lee's view, and I don't want to say more about it than I do know, is that he's looking for a view on which these notions of fundamental, these notions of passage and flow and so on are somehow absolutely fundamental to our physical description of the world. And that's going to be a very, very different picture than the kind we're presenting.
I wonder how presentism works there, but let's leave that for another occasion. I just want to say this, whenever this bit about time comes up, what comes to my mind is a poem that some of you may know called The Paradox of Time by some guy named Arthur Dobson, I think is his name, or Henry Austin Dobson. It has the line in it, "Time goes, you say, alas, time stays, we go." I like that a lot because the Mentaculus picture is one of the block universe. There are events that occur spread out to a block universe. So we are going in the sense that we occupy different locations in the block universe at different times, but time isn't going anywhere. Time isn't passing.
I'm not sure exactly in what sense it's true that we occupy different locations at different times. We occupy a certain worm in.
Yeah, that's all I mean.
That's what
I don't mean anything different
occupy
from
that
that.
timelessly.
I didn't mean that we are something over and above the worm.
Okay.
You and I are both worms, or anyway, we'll be eaten.
or lower, right.